In this video, the self-developed computer application LEMOHR is used to demonstrate how stresses and strains are linked, what a plane stress state and a plane strain state are, how Mohr circles are constructed for a plane stress state and for the general three-dimensional stress state, and how failure theories can be applied in this context. The LEMOHR application is divided into a 2D and a 3D version. First, an infinitesimal cube is cut out of the body as shown on the left, and only the xy plane is considered. Stresses are forces per area, and therefore the stresses sigma x and sigma y are shown in red, acting perpendicular to the cut faces. Since they act perpendicular, in other words normal to the respected surface, they are called normal stresses. The shear stress tau xy, shown in green, acts parallel to the cut edges. Because stresses occur only in the xy plane, this is referred to as a plane stress state in the xy plane. Sigma x, sigma y, and tau xy are components of the stress tensor, shown here for the general three-dimensional case. Both notations are equivalent, and on the following, the notation on the right will be used. The diagonal entries represent the normal stresses, and the entries above and below the diagonal represent the shear stress components. The stress tensor is symmetric, meaning that the entry in 3,1 is identical to the entry in 1,3. The plane stress state can now be represented in a stress diagram, with the normal stress state sigma on the horizontal axis and the shear stress tau on the vertical axis. The points sigma x, tau xy, and sigma y minus tau xy form 2 points in this diagram, shown here in red. Connecting these points with a straight line yields an intersection with the horizontal sigma axis. Using this intersection as the center and the distance to one of the red points as the radius, the Mohr circle for the xy plane is obtained. Because a plane stress state in the xy plane implies that the third normal stress sigma z is 0, 2 additional Mohr circles can be constructed. Both intersect the sigma axis at the origin. The Mohr circle of the yz plane has its second intersection at the smaller of the two sigma axis intersections of the already constructed circle. The Mohr circle of the zx plane is bounded by the largest and smallest possible normal stresses. The 3 intersection points of the circles with the sigma axis correspond to the principal normal stresses, which will be referred to simply as principal stresses. Principal stresses are always ordered by magnitude such that sigma 1 is always greater or equal to sigma 2, which is always greater or equal to sigma 3. If the infinitesimal cube is viewed at the angle phi PAS, it is oriented in the principal axis system. The principal axis system is the coordinate system whose axes align with the principal directions, where the shear stress components vanish and the normal stresses become maximal. The resulting normal stresses sigma 1 and sigma 2 are the principal stresses. The direction of rotation is reversed compared to Mohr circles. A rotation about the 3 axes in the mathematically positive sense, here counterclockwise, corresponds to a clockwise rotation in Mohr's circle, and by a factor of 2. This factor of 2 arises from the coordinate transformation relations. To derive the transformation equations, the material point is first cut along a plane inclined by the angle phi. This introduces the xi-eta coordinate system and the corresponding normal and shear stresses. Then the force equilibrium is formulated in the xi and eta directions. From this, the transformation equations for an in-plane rotation can be derived. For the principal axis system, it holds that no shear stresses act in the system. If tau eta xi is set to 0 and the third equation is solved for the angle phi, this equation is obtained. With it, the rotation angle of the principal axis system relative to the global load coordinate system can be determined analytically. This makes it possible to validate the rotation angle that was obtained graphically using Mohr circles. The transformation relations can also be rearranged into this equation. This allows the principal stresses to be computed analytically. Again, it is important to respect the previously mentioned ordering of the principal stresses, such that sigma 1 is always greater or equal to sigma 2, which is always greater or equal to sigma 3, always holds. The transformation equations can also be used for an arbitrary free rotation in the plane. In this case, the normal and shear stress components of the stress tensor are computed for rotation by the angle phi. The representation of the stress state in Mohr circles enables a graphical determination of the stress components for any in-plane rotation of the considered cut surface. The key takeaway is this rotation is represented by a movement along the circle's perimeter. A rotation by phi x tilde therefore corresponds in Mohr circles to a rotation along the circle by 2 phi x tilde in the opposite direction. The normal stress component sigma x then becomes sigma x tilde. Likewise, the shear stress component tau xy becomes tau x tilde y tilde, and the same applies to sigma y. These components are shown here in the stress tensor of the rotated system. The same applies to a rotation out of the principal axis system, in other words, from the horizontal axis in the stress diagram. If only one component of the prescribed plane stress state is changed, for example, if sigma y becomes negative, then the intersection point of the Mohr circle of the xy plane may lie to the left of the origin, because the plane stress state in the xy plane still implies that sigma z equals 0. One principal stress lies at the origin. Therefore, the Mohr circle of the xy plane is no longer bounded by sigma 1 and sigma 2, but by sigma 3 and sigma 1. Corresponding to the 3-1 plane in the principal axis system. The largest Mohr circle is always the one bounded by sigma 3 and sigma 1. If the second prescribed normal stress sigma x is also changed such that it becomes smaller than sigma y, then the assignment of principal stress planes in Mohr circles to the planes of the load coordinate system changes again. A special case occurs when only the shear stress tau xy is prescribed. In this case, the Mohr circle of the xy plane has its center at the origin, and the Mohr circles of the other principal planes result from appropriately connecting the principal stresses. Since this stress state is rotated by 90 degrees from the principal axis system on the Mohr circle, it follows that the maximum shear stress in the infinitesimal cube occurs at an orientation of 45 degrees relative to the principal axis system, or equivalent that the principal axis system is rotated by 45 degrees relative to the load coordinate system. Stresses cause strains in the material. Shown here is a disk made of linear elastic isotropic material, which is subjected exclusively to a uniaxial normal stress sigma x. There are no geometric constraints here, such as a rigid die. If this normal stress is positive, the component elongates along the x-axis by delta L, and due to lateral contraction, it becomes narrower in the y direction by delta H. Assuming small deformations, the undeformed disk is shown in gray and the deformed shape is outlined in blue. The magnitude of the strain therefore describes the relative change in a body's dimensions, that is, the change in the length delta L relative to the initial length L0, and so on. This exact case is set in LEMOHR here, with a uniaxial normal stress sigma x greater than 0. Since this normal stress state is the only stress present, and since it is not a shear stress, the system is also in the principal axis system. Thus, the normal stresses are simultaneously the principal stresses. Using this switch, LEMOHR displays the deformed shape of the disk based on the material parameters specified here for Poisson's rate, Young's module, and the scaling factor. If the uniaxial normal stress is negative, the disk deforms accordingly, as shown here. This demonstrates that a stress acting along one axis leads to strains along multiple axes. Formally, this is described by Hooke's material model, which is rearranged here in terms of strains. It applies to elastic reversible processes, and there are extensions for thermal effects and so on. According to Hooke's law, a uniaxial normal stress even produces strains along all three axes. Thus, a uniaxial stress results in a three-dimensional strain state. For the special case of pure shear stress in a plane, the disk deforms as shown here. A shear stress acting in a plane produces only a shear strain, as follows from Hooke's material model.